Dear students, welcome again in this new video, and today we will discuss a very important topic, differentiability of functions. First of all, derivative at a point. Suppose f be a function with domain D. The derivative of f at a point x of its domain D is defined as limit as h equals to 0 f x plus h minus f x upon h, provided the limit exists and is finite. This derivative is denoted by f dash x or d upon dx of f x. The derivative of f at point C in its domain is also defined as f x minus f c upon x minus c, limit as x approaches to c, provided this limit exists and is finite. This derivative is denoted by f dash c, derivative of f x at point C. Now, if x approaches to c from left, then derivative is called left hand derivative and is denoted by L f dash c or f dash c minus 0. If x approaches to c from right, then it is known as right hand derivative or RHD, right hand derivative, and is denoted by R f dash c or f dash c plus 0. The derivative at a point exists if left hand derivative and right hand derivative both exist and are equal. A function f is said to be differentiable at a point C if and only if the derivative of f exists at point C. The process of finding derivative of functions is called differentiation. Now, derivative in an interval, a function is said to be derivable in open interval AB if f is derivable at each point of this open interval AB. If further, if f is derivable from the right at point A and from the left at point B, then f is derivable in the closed interval AB. Now, see this article. Every real valued function which is derivable at a point of its domain is also continuous at that point. Suppose that f is derivable at point C, then f dash c, according to the definition of differentiation, limit as x approaches to c f x minus f c upon x minus c. This limit is finite, is denoted by f dash c. Now, f x minus f c can be written as by multiplying and divided by x minus c, we get f x minus f c upon x minus c into x minus c. Taking limit as x approaches to c, limit of f x minus c as x approaches to c will be equal to limit of f x minus f c upon x minus c into x minus c as x approaches to c. This limit is equal to f dash c, and in this limit when x approaches to c, this x minus c approaches to 0. Therefore, limit of f x minus f c as x approaches to c is equal to 0. That is, limit of f x minus f c as x approaches to c equal to 0 means limit of f x as x approaches to c is equal to f c. That is, limit of function at point C is equal to the value of function at point C. Therefore, function is continuous at C. Now, differentiability and differentials. A function is said to be differentiable at a point x of the domain AB if it is finite and determined in any neighborhood of that point, if the increment delta y in the function corresponding to every arbitrarily assigned increment delta x in x is expressed in the form y is equal to f x, and if there is a small increment in the value of x, then corresponding increment in y will be equal to delta y plus delta y. Now, no, suppose this is equation number 1, this is equation number 2. Now 2 minus 1 gives delta y will be equal to fx plus delta y minus fx. Delta y will be equal to fx plus delta y minus fx. This can be written as a into delta x plus epsilon into delta x, where a is independent of delta x and epsilon is a function of delta x which approaches to 0 as delta x approaches to 0. Now this first equation can be written as delta y is equal to a delta x plus epsilon delta x. Now from equation first, if we divide both sides by delta x, then delta y upon delta x will be equal to a plus epsilon. Now taking limit as delta x approaches to 0, limit of this delta y upon delta x as delta x approaches to 0 comes out to be a, because epsilon approaches to 0 as delta x approaches to 0. Therefore this constant is known as differential coefficient of y at point x y. Now the necessary and sufficient condition for a function to be differentiable at a given point x is that function fx possesses a finite derivative at that point. Now condition is necessary. Suppose that fx be differentiable at a given point x, then fx plus delta x minus fx can be written as a delta x plus epsilon delta x, where a is a constant independent of delta x and epsilon is a function of delta x as delta x approaches to 0, epsilon approaches to 0. Now fx plus delta x minus fx upon x can be written as delta x. Delta x can be written as a plus epsilon. Now limit as taking limit on both sides as delta x approaches to 0, fx plus delta x minus fx upon delta x will be equal to 0 as epsilon approaches to 0 as delta x approaches to 0. This is the derivative of function f dash x is equal to a. It means fx possesses a finite derivative at x equal to a. Now condition is sufficient. Let fx possess a finite derivative f dash x at x, then limit as delta x approaches to 0 of fx plus delta x minus fx upon delta x will be equal to f dash x, which is a finite number. Put this fx plus delta x minus fx upon delta x minus f dash is equal to epsilon, and epsilon approaches to 0 as delta x approaches to 0. This means fx plus delta x minus fx will be equal to delta x into f dash x plus epsilon delta x. This means fx is differentiable at x equal to at any point x. No, Darbox theorem. If fx is derivable for every point x in a closed interval ab and f dash a, f dash b are opposite signs, then there is at least one point x not in the interval ab such that f dash x is equal to 0. Without any general loss of generality, we assume that f dash a is of positive sign and f dash b is negative. Now put f x delta x is equal to f x plus delta x minus f x upon delta x, because f x is derivable in the closed interval ab. Therefore f x is continuous in this interval, and this function capital F x delta x is continuous in this closed interval ab for any delta x not equal to 0, because f dash a and f dash b are of opposite sign and capital F x delta x is also a continuous function in the interval ab. This means f x delta x must vanish at some point x naught lying between a and b. that is f x naught delta x approach to 0, that is f x naught plus delta x minus f x upon delta x is equal to 0, that is f dash x naught is equal to 0. Now we discuss some examples. Suppose f is differentiable at point A, then evaluate this limit of x square f a minus a square f x upon x minus a as x approach to a. We put x is equal to a plus h, so that h approach to 0 as x approach to a. Now limit of x square f a minus a square f x upon x minus a as x approach to a is equal to limit of, we have put x is equal to a plus h, then this limit becomes equal to a plus h square f a minus a square f a plus h upon a plus h minus a as h approach to 0. Now if we expand this square of a plus h, we get a square plus 2h plus h square into f a minus a square into f a plus h upon h limit as h approach to 0. This will be equal to limit as h approach to 0 a square f a plus 2h into f a plus h square into f a minus a square f a plus h. Taking common h from these two terms, we get h into 2a f a plus h into f a, and taking a square from these two terms minus a square common, f a plus h minus f a upon h. Now this h cancelled out from these two terms, limit h equals to 0 to f a 2a f a plus h f a minus a square f a plus h minus f a upon h. Take limit as h equals to 0, limit of this 2 f a will be equal to 2a f a, and limit of h f a will be equal to 0 because h equals to 0, and a square, and limit of this f a plus h minus f a upon h will be equal to f dash a. So this limit will be equal to 2a f a minus a square f dash a. Now we have to prove that fx is equal to x minus 3 modulus has no derivative at point x equal to 3, and also in the second question, if fx is equal to x sin 1 by x as when x is not equal to 0, and fx is equal to 0 when x is equal to 0, then we have to show that f is not differentiable at point x equal to 0. And another question, we have to prove that the greatest integer function x is not differentiable at point x equal to 1. Now see this first equation, fx is equal to x minus 3, and we have to prove that this is not derivable at x equal to 3. Now left hand derivative of fx as at x equal to 3 will be equal to limit as x goes to 3 from left fx minus f3 upon x minus 3. Fx is equal to x minus 3 by putting the value of fx and by putting the value of f3. F3 is equal to 0. F3 is equal to 0 because f3 will be equal to 3 minus 3 modulus is equal to 0 upon x minus 3. For left limit, we put x is equal to 3 minus h. H is a positive small number, as x equals to 3 from left, h equals to 0. And this will be equal to limit as x equals to 3 from left, x minus 3 modulus upon x minus 3. We put x is equal to 3 minus h. We get this limit equal to as h equals to 0 minus h modulus upon minus h. This comes out to be minus 1. Similarly, right hand derivative is equal to limit as x equals to 3 from right, fx minus f3 upon x minus 3. By putting the value of fx and f3, we get x minus 3 modulus minus 0 upon x minus 3. For right limit, we put x is equal to 3 minus h, 3 plus h, where h is a very small positive number, as x equals to 3 from right, h equals to 0. This limit becomes equal to limit as h equals to 0, 3 plus h minus minus 3 upon modulus upon 3 plus h minus 3. After simplification, this is equal to limit as h equals to 0, h modulus upon h, this comes out to be equal to 1, because left hand derivative is not equal to right hand derivative, therefore fx is not differentiable at x equal to 3. Now see this question, fx is equal to x sin 1 by x as x is not equal to 0, and fx is equal to 0 and when x is equal to 0. Now we have to prove that this function is not differentiable. Now right hand derivative of this function, fx minus f0 upon x minus 0 as x equals to 0 from right, because we have to find the derivative of function at x equal to 0. This limit will be equal to, by putting the value of fx is equal, which is equal to x into sine of 1 by x minus f0 the value put कर रहे हैं f0 upon x, this will be equal to, this cancel out, limit sine of 1 by x, and limit sine of 1 by x does not exist as x equals to 0, therefore right hand derivative of this function does not exist, therefore function is not derivable at x equal to 0. Now for this function, greater integer function of x, when x equals to we have to find the derivative of this function at x is equal to 1, therefore left hand derivative of fx when x equals to 1 from left will be equal to limit of x equals to minus 1 now we are evaluating the left hand limit. For left hand limit we put x is equal to 1 minus h, where h is a positive number, real number, and h equals to 0 as x equals to 1 from left. This will be equal to limit h equals to 0, 1 minus h greatest integer, and greatest integer of 1 minus h will be equal to 0, and this limit comes out to be 0. And similarly right limit comes out to be 1. This means left limit of function is not equal to right limit. This means function is not continuous, and we know that if function is not continuous, then function will be not differentiable at that point. So students, these are some examples in which we have studied about the differentiability of functions. In the next video we will continue this topic by taking some more examples. Thank you students.